Okay, so the plan today is to go over what we went over like in the last session, reactions of conjugated dienes practice, and then do a Kahoot on the alkene-alkyne reactions and also the newest stuff here with the conjugated dienes, and then move on to Diels-Alder. Right. So let's go on to conjugated dienes. We know what is the definition of a conjugated diene? What is that structure in the molecule? Conjugated diene. Right? So conjugated means resonance. Diene means that we have two alkenes. So conjugated means that it could do resonance. Di meaning two. Ene meaning alkene. So we have two alkenes right next to each other that can do resonance. So an example, some examples would be like that. This is one example because we see this alkene here is right next to that alkene, where you notice how all of these carbons here of the alkene or the molecule are sp2, 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 sp2. Since there's a network of sp2 atoms, they could do resonance with each other, right? So an example of resonance is that where we move this double bond to make a double bond here. When we do that, we have to move this double bond to make a lone pair of electrons there. Right? That is going to make this resonance structure here. Right? Another example of a conjugated diene could be in a ring. So let's say, for example, you have something like this right here. This is considered a conjugated diene because we see that the carbons of these alkenes here are sp2 hybridized. So we have a network of adjacent sp2, sp2, sp2 atoms, making them conjugated right there. Right? Something that is not conjugated would be something like this, where there is an sp3 roadblock. So if there is an sp3 atom between alkenes, this diene here is not conjugated. This is unconjugated. So this is an unconjugated or an isolated unconjugated diene or isolated diene because they are not close to each other. They're not conjugated. They cannot do resonance. Okay. And with the reactions of conjugated dienes that you could do are addition of HX or X2, right? And you also get two different kind of products, the thermodynamic product and the kinetic product. So the thermodynamic product will be the more stable product, like more stable alkene in this case, right? The kinetic product will come from the more stable intermediate. Right? Where in future reactions, you are going to get thermodynamic product and kinetic products, but for conjugated reactions, like the addition of HX and X2, the intermediate is going to be a carbocation. Other intermediates in other reactions could be carb anions, the negative charge, or radicals. But for these reactions here, we're just going to worry about the carbocation. Okay. Yeah. So let's do an example problem of that. Let's say we have this conjugated diene here and react that with DCl. When you see D here, that is just an isotope of hydrogen, H. That is deuterium ion, right? The reason why you might see that D is because they want you to draw out that deuterium on the product. If they give you HCl, you could draw the product where the H is invisible. You can leave the H out. But if you see D, you can't leave that as invisible. You have to draw out that D, right? So we have two alkenes here, and both of them are going to, let's say, react with this DCl. But since this is symmetrical, right? Like this is a symmetrical system, it wouldn't matter which alkene we reacted with. If we reacted with this alkene, it will give us the same intermediate as if we reacted with this alkene here. So let's just focus on the bottom alkene. We want to form the more stable carbocation first, which is going to be this more stable position here, right? If we want the carbocation in that position, we want to protonate this less substituted carbon. So let's draw out the DCl. Oh, shoot, it's getting dark. Do you guys want the lights off or on? That's good. On? Okay. Yeah, okay. Okay. Yeah. Right. So we want to make the more stable carbocation. The less substrate is going to get protonated, pick out the Cl. This forms our more stable carbocation intermediate right here. This carbocation is not only tertiary, but it is tertiary allylic. And allylic means that it is one carbon away from a double bonded carbon. That is allylic, right? Where that tertiary allylic carbocation can do resonance with the double bond nearby. So that double bond can move there, giving us this resonance structure here. This carbon here gained the bond, so it is now neutral. This carbon right here lost the bond, so that carbon has a positive charge, like that. Okay. Oh, and also, we said that this carbon grabbed the deuterium, so we have to draw out that deuterium right here. We can't leave that as invisible because that is not hydrogen. That is an isotope of hydrogen. Right? So that deuterium is also here on that resonance structure as well. If it was HCl instead, then you didn't have to draw that H out. But this is DCl, so you have to draw out the D explicitly. You can't leave the deuterium as invisible. Now, once we get our best resonance set, we have to now determine which one will give us our thermodynamic product and which one will give us our kinetic product. So to do that, let's classify the carbocation and double bonds. We already classified this carbocation, which is tertiary allylic. The carbocation here is primary allylic. Right? Now let's classify the double bond. What kind of double bond is this right here? Like, what is the substitution? Is it unsubstituted mono, di, tri, tetra? Di substituted, right? Because there are two R groups. So di substituted. What about this double bond here? Yep, tetra. So based on that, which one would give you your thermodynamic product? Would it be the left one? The right one here, right? The right one here is going to give us our thermodynamic product because it gives us the more stable double bond. So this is the thermodynamic. Well, the intermediate that will give us the thermodynamic product, and the left side will give us the kinetic product because it came from the more stable intermediate, more stable carbocation, right? To finish up this reaction, let's say the Cl minus comes in, attacks that carbocation, and give us this kinetic product here. Oh, and let's say the Cl minus here attacks that one to give us this thermodynamic product here. where this is our thermodynamic product because this is our most stable double bond. This is our kinetic product because it came from the more stable intermediate. There was a carbocation right here, which was the most stable carbocation intermediate here. Okay. Yeah, thermodynamic is when it is really hot, high temperature, right? Yeah. Right, when it's hot. And when it's cold, low temperature, then that's when the kinetic product is favored. Yeah. Oh, right. So there is a chiral center here. This one here would be racemic. But this product here would not be racemic because there are no chiral centers. Right, so the thermodynamic product, no racemic mixture, no chiral center. The kinetic product would give you a racemic mixture. So it depends on your molecule and if there are chiral centers or not. Yes, a thermodynamic product. Oh, it depends on your temperature. Like on your arrow, you have some kind of temperature. Did Pascal say what temperature favors thermodynamic? Oh, 70, about 70, at least 70. Okay. I see. Okay. So at least 70 degrees Celsius will give you the thermodynamic product. If you are below 70 degrees Celsius, this will be your major product. Yeah. Right. Right. So the kinetic will come from the more stable intermediate, but it doesn't have to be hyperconjugation because there could be some tricky problems like this. Like let's say we have um, this resonance structure. Right. Oh wait, actually. Oh yeah, yeah. In that case, yeah, it will always be the conjugation because if we do the resonance structure, both of them would be allylic, and since both of them are allylic, then we don't have to worry about the resonance of that. Yeah, radicals and carb anions. Yeah, carbocations, carb anions, and radicals. Where this first one here gives you your thermodynamic product. The second one here gives you your kinetic product. Uh-huh. Oh, right, yeah. I planned to go to lecture today, but I overslept, so I didn't go lecture today. I didn't hear what he said, but I'll see it in his notes when he posted it. Yeah, thank you, thank you. I'll go next week. Right? Yeah. So, right. Let's see. Now, let's try this example here. Now, this is an asymmetrical conjugated diene, where this is our conjugated diene system here. The benzene would not react with the HCl because when you see a benzene ring, that is an aromatic ring that is really stable. We do not want to break that aromaticity, so that's going to stay unaffected. The thing that is going to react is one of these double bonds here. Right. So instead of drawing both resonance structures or resonance sets, let's look at all of the carbons of this conjugated diene here. Which one of these four carbons will give you your most stable carbocation? Wait, don't do that trick. That trick is not good all the time. So let's just do it one at a time. Let's focus on this alkene here. We know that this carbon here will give us the more stable carbocation. So we want to protonate the less stable, less substituted side. when we do that, we are going to get that carbocation right there. This carbocation is secondary allylic, where we could do resonance by moving that double bond right there. And that would give us that carbocation right there. Okay. Now let's focus on the other alkene. This one here is tricky because both carbons look like they are equally substituted, right? But there is one carbon that is going to give us the more stable carbocation. And do you guys know which one that is? Great, the left one, because if there was a carbocation right here, that carbocation can do a lot more resonance with the benzene ring. The right carbocation can only do resonance with one double bond. The left carbocation can do resonance with 3 double bonds here. So if we want the carbocation on the left side, we are going to protonate the right side. So that right side is going to grab the hydrogen, kick out the Cl, and give us that carbocation right there on the benzylic position. This is the benzylic position because it is right next to the benzene. Right there. Right. That can do resonance with the okay, so in this case, this resonance structure right here, if we moved this double bond to that right there, that would give us this resonance structure, but that is not a good thing because that would break the aromatic ring, right? This is the resonance structure of that, which this is no longer aromatic. So that is less stable. So we're not going to get that carbocation, we're going to get the other carbocation because this resonance structure here will break the aromatic benzene ring right there. Yeah. Oh right, like we want the benzene to like stay the same. Like we don't want to interrupt the aromatic ring. Wait, well, your question was like we don't want to disrupt it, or right, yeah. This is the most stable carbocation intermediate because it is right next to the benzene. But we do not want to like break the aromatic ring and do resonance there because that's gonna break the aromaticity and break the stability, right? So if that's the case, we want the carbocation to be here instead. So let's redo this set right here. Instead of that carbon attacking the hydrogen, this carbon is going to attack the hydrogen, kick out the Cl, and give us this carbocation here instead. Like that. And that one, we could do resonance. That. And that is going to give us that carbocation right here. Okay. Now, we have 2 sets here. We have to choose the set that gives us the most stable carbocation intermediate. So let's classify each one. This one is secondary allylic. This one here is secondary benzylic and allylic because it is right next to the benzene and the alkene. This one here is secondary allylic. This one here is primary allylic. Since we know that this is the best carbocation because it is benzylic and allylic, this is our best resonance set right here. That means that we are going to ignore that set right there, right? And now, based on that, there's only going to be one kinetic product here, which is the more stable carbocation intermediate, the secondary benzylic and allylic carbocation. But the thermodynamic product, these two would be thermodynamic. Or no, there's actually one that's going to be thermodynamic. And which one do you guys think that is? Is this double bond more stable, or is this double bond more stable here? They're both di substituted, right? But there's one double bond that can do resonance. Yeah, the one on the left, because it is right next to the benzene ring, which can do resonance. So this is going to be your thermodynamic product. This is going to be your kinetic product. So thermo, and this is kinetic, where the Cl is just going to attack that carbocation right there. So your thermodynamic product gives you your more stable double bond. And Cl is there. Kinetic product comes from the more stable intermediate. In this reactions, it is the carbocation, more stable carbocation right there. This is kinetic. This is thermodynamic. And it doesn't have to be HX. We could have reacted with X2 halogenation. So let's say we have this conjugated system here. And we react that with Cl2. Let's focus on this right alkene, where the mechanism is going to be the same as the halogenation. One of the carbons is going to attack that halogen, kick out that leaving group, and at the same time, the halogen that is being attacked is going to attack the other alkene, forming your chloronium ion ring, that ring like epoxide-like structure. Like this right here. In chapter 12, when we did this reaction, the nucleophile, which could be Cl minus, or if we had water or alcohol, it would attack the more subside and break open the ring right away. But in this chapter here, that doesn't happen first. Think of it as an SN1 reaction now, where this is a good leaving group, and it could just leave by itself. It could just break open by itself to form the more stable carbocation. So if that's the case, which carbon of the ring is going to be more stable? It's going to give us the more stable carbocation. Right, the bottom one, even though they're both equally substituted, the bottom one here is allylic because it is right next to the double bond, and because it is allylic, it could do resonance. So we're going to break open the ring this way. Cl, positive charge here. Okay, now we have our resonance set by moving that double bond there to give us that resonance structure. Now from here, we determine which one will give us our thermodynamic product and which one will give us our kinetic product. Oh, that was the first set of this alkene here. There's still this double bond where we have to consider that set as well. So let's say we do the same mechanism for the other double bond, pick out that chlorine, do that, we would get this ring right here. Double bond there, ring here, ring here. We see that this carbon here is going to give us the more stable carbocation. So we're going to break open the ring like that for this resonance set here. Oh, positive charge here. Okay. Now this is a tertiary allylic carbocation. When I draw the resonance structure of that, I move the double bond there and get this resonance structure here. Carbocation there. Okay. Now, this resonance set here, the first one, came from that double bond. This bottom resonance set came from this double bond here. Now, we have to determine which one is our best resonance set. Which one has the most stable carbocation intermediate? Right, the bottom one, because this bottom one here has a tertiary allylic carbocation, whereas the top one here does not have a tertiary allylic carbocation. This is secondary allylic, which is less stable than that tertiary allylic. So we are going to eliminate the top one, ignore that one. We only focus on the bottom one now, where now we determine which one is our kinetic product, which one is our thermodynamic product. Great, kinetic is on the left because it comes with a more stable intermediate, and thermodynamic is on the right because it forms the more stable alkene product. So the Cl- is just going to come back and attack to finish up the reaction. Thermal product. So kinetic products. And you only draw one of these depending on the temperature. If you are at least 70 degrees Celsius, 70 or higher, this would be your major product. If you are below 70 degrees Celsius, then this is your major product. The kinetic product happens in low temperature. Thermodynamic product happens in high temperature. Yeah. Right. Stereochemistry is not conservative because of the carbocation here, the flat sp2 carbocation. Back in the chapter 12, the halogenation X2 was always anti-addition because from this ring right here, the nucleophile would attack right away and invert stereochemistry, making that anti. But in this case right here, we form a carbocation, which loses all stereochemistry, and now it's randomized. So there's no anti or syn addition in this reaction here. Okay. Yeah. Yeah. All right. I broke this side because that would give me this carbocation right there with the chlorine here. If I broke open this side, I'm going to get this carbocation right here. They look like they are equally substituted. They are secondary, but then we look at which one is allylic, which one can do resonance. Right, the bottom one here, this carbocation is too far away from the double bond here. The top one, the double bond is here. Right next to that are the allylic positions. So since we know this is the double bond here, the allylic positions are either here, here, or here. Right, we're looking for the more stable carbocation to break open the ring to make us the more stable one. Yeah. Right. You understand how we got these resonance sets, right? Right. So once we have our two resonance sets, we have to eliminate one. And we choose the one that gives us the more stable, that has the most stable intermediate. Right. This is the one that has the most stable intermediate because this is tertiary allylic. These ones here are less stable than that one. Right. Now I'm gonna give you guys one practice problem on this one and try it on your own, and then we'll move on to the Kahoot. Try this one. Oh, and for these problems that we've been doing here, I didn't give you temperature because I wanted to show both the kinetic and thermodynamic products. But on the exam, you'll most likely have some kind of temperature on the arrow where you only draw one of the products, either kinetic or thermodynamic, depending on the temperature. But practice drawing both the kinetic and thermodynamic for these practice problems. All right. Yeah, that's the shortcut, like the 1,2 addition, 1,4 addition. Um, it depends on the molecule. Because for kinetic, it's always going to be 1,2. You can always say for kinetic, it's always 1,2 addition. But for thermodynamic, it could either be 1,2 or 1,4, depending on what's around it. Right. So I don't like teaching it that way because some people just always think that the thermodynamic is always 1,4, but that's not always the case. Oh, right. So this is the first set, this is the second set, right? Yeah. But since it's symmetrical conjugate Diene, yeah, they're the same. So we don't have to eliminate one. Right. Yeah. If it was asymmetrical, then you have to compare the two sets. Okay, so X2 here, we react with the double bonds. Let's look at this double bond here, where it will form that bromonium ion ring first. Once we have our bromonium ion, think of this as a good leaving group because it is allylic next to a double bond, right? This leaving group could just leave by itself first, where we have to choose which bond will break open the bromonium ion. We want to break the bond that will give us the more stable carbocation, which is this carbon right here, because it is tertiary allylic. Since we want the carbocation there, we want that carbon to lose a bond. So we're going to break open the ring that way to make that carbon lose a bond and give us our more stable carbocation. That carbon lost the bond, which is why it has a positive charge now. The carbon nearby is still attached to that bromine. And we still have an alkene right there. Okay. This carbocation here is tertiary allylic, where it could do resonance with the double bond nearby. So when we draw that resonance, we get this structure here. With the positive charge on this carbon, because that carbon lost the bond when we removed that double bond here. So that's the resonance set for that double bond right there. So you guys notice how this is like symmetrical right here? If we try to make the resonance set for the other double bond, we're going to see that we are making the exact same resonance set, right? Like let's say we react with the top double bond, which is going to be like this, form the bromonium ion here, positive charge, break that double bond, and then break that ring that way to form the more stable carbocation intermediate, put the bromine there, tertiary allylic carbocation, can do resonance with the double bond there, gives us this resonance structure here, right? Where these resonance structures are the same. Like this set is the same as that set because of the symmetry here, right? Where this tertiary allylic carbocation is the same thing as this tertiary allylic carbocation, because these structures are just flipped upside down. This is the same structure as this, it's just flipped upside down. So if you have a symmetrical structure, you only have to worry about one set. If you have an asymmetrical structure like we had previously, right? Draw out two sets from your two double bonds and choose the set that has the most stable carbocation and ignore the other set. Right? But in symmetrical molecules, we only look at one set because both sets are the same. So based on these resin structures, yeah. Oh, there technically is like there could be wedge or dash, right? But I didn't include it there because I know that that bromonium ring is going to break open and form a carbocation there, which makes everything flat and planar and it loses all stereochemistry. Yeah, no sin addition. Chapter. For conjugated diene, yes, there's no sin addition or anti-addition for conjugated dienes. For Diels-Alder, the stereochemistry is a little bit more complicated, but I'll go over that when I go over Diels-Alder and the regiochemistry as well. Yeah, yeah. For these ones here, leave everything planar. Yeah. When he went over Diels-Alder, did he go over dienophile? Did he talk about electron donating group, electron withdrawing group? Oh, okay, that's good. Right, more reactive, right. Let's see. Did he go up to endo-exyl row? Oh, yeah, S trans, yeah. Oh, homo-lumo orbitals. I see. Oh, yeah, the last CR7, I went to the basics of Diels-Alder, like the diene, dienophile, but I didn't go deeper into it. I didn't talk about like EDG, electron donating group, electron withdrawing group. Yeah. Oh, really? Oh, dang. Okay, yeah. Yeah. To know it for the exam. Yeah. I gotta review that homo stuff too because that's more like PChem, like the orbital stuff. But I'll review that for the next session. We'll just go over like the regiochemistry, stereochemistry, OChem part of the Diels-Alder today, and then I'll go over the homo stuff for next session. Yeah. Okay. So which one of these resin structures here would be the thermodynamic product, and which ones would be the kinetic product? Great. The left one, because that has the tertiary allylic carbocation. Thermo would be the right because it has the tetra substituted double bond, which is more stable than the tri substituted double bond. And this tertiary allylic carbocation is more stable than the secondary allylic carbocation. The Br minus is just going to come back, attack to give us our final answers. No stereochemistry because it attacks a flat carbon. So it could be wedge or dash, so no sin or anti-addition here. That's the kinetic product. You draw that product out if you are below 70 degrees Celsius. If you are at least 70 degrees Celsius, then you draw out this product here. This is Celsius. This is going to be less than 70 degrees Celsius. Okay. Now, let's see. Let's move on to the Kahoot. the reason why I made this Kahoot is because like I didn't know when Pascal was gonna stop, because I think I was like going ahead a little bit too much, so I didn't want to like go too ahead because I didn't want to overwhelm you guys. So I just made this Kahoot to review the old material, like the Alkyne, but we'll just get this done and then move on to Diels-Alder. Oh, nice. Okay, let's see. Right. So this right here is a good leaving group, tertiary substrate, and we have a strong base, CH3, CH2O minus, which is small and unhindered, right? So if it's small and unhindered, we look for the Zaitsev alkene, which is going to get the most substituted beta hydrogen, right? And this beta hydrogen here is dash because this is a wedge methyl, and that dash hydrogen follows the anti-periplanar transition state because it is opposite to the leaving group there. So we're able to get that hydrogen, make a double bond there, kick that good leaving group out. This right here is the less substituted beta hydrogen, which will give you the less stable double bond. You would get that if you have a bulky base like butoxide or LDA, or if this hydrogen here was not anti-periplanar to that leaving group, and you can't rotate it because it's in a ring. Right, E2. There is sound. What the heck? Ooh, half and half. Okay. Oh, okay. So we have an internal alkyne here, and there are three reducing agents that we can do to reduce this alkyne: H2PDC, H2 Lindlar's catalyst, and this dissolving metal reduction thing here, sodium metal and ammonia liquid, right? H2PDC will completely reduce this alkyne to the alkane. Everything's gonna be single bond. H2 Lindlar's catalyst, which is a poison catalyst, slows down the reaction and stops at the cis alkene. This sodium metal here, or lithium metal with ammonia liquid, will make the trans alkene, right? And then from the trans alkene, these two sets of reagents here is dihydroxylation, which makes two alcohols on the same side, which is this answer right here at the trans configuration. Right? This would be if we had H2 Lindlar's catalyst instead. Any questions on this? Okay. Yeah. If you guys just joined, you guys could join the game through this code right here. We got like, yeah, a lot more questions left. Nice, nice. So we have an internal alkyne, sodium or lithium metal with ammonia liquid reduces that alkyne into the trans alkene, which is this trans alkene right there. Yeah. Right. We need two equivalents of sodium because somewhere in the mechanism it forms a radical and a lone pair of electrons on the other carbon, right? That lone pair of electrons, negative charge, is going to get protonated by the ammonia. But we still have one radical somewhere in the mechanism. That radical is going to become a lone pair of electrons, like a full negative charge, with the other second equivalents of sodium or lithium metal, and mix that into a negative charge, and then reprotonate that with the hydrogen. It would be more clear if we look at the mechanism, which I think I went over that during the alkyne CR, like the constant reveal CR6. But you see why we need two equivalents of that metal in the mechanism. Oh, wait. So yeah, it's the trans because it has less steric hindrance here. The two R groups are away from each other. And since there's less steric hindrance, it's more stable. Right? Because in the mechanism, we form a radical and a lone pair of electrons, which it prefers to be in this position because it is more stable. This right here, if you use H2 Lindlar's catalyst, it's supposed to be in a cis, even though it's less stable, is because you know how for hydrogenation, it's syn addition, where we add hydrogens on the same side. The hydrogens here will have to be cis to each other. forcing the two R groups to be cis to each other as well. Right? Yeah. So if you see 2EQ or excess, then it will go through of sodium or lithium metal. I might have to write this one on the chalkboard to explain. Okay, mix answers. Yeah. I try to make tricky answers here as well. This is, yeah, with these reagents, that's not the answer. If that wasn't there, then that would be the answer. Yeah, which is this one here. That's right. So, yeah, explain the whole thing. Yeah, because I knew this was going to be the tricky one because of the regiochemistry and everything. So I gotta explain it here. So when you see HBr and roar, right? This roar thing, think of anti-Markovnikov. Which means that we're gonna add the bromine on the left subside of the alkyne. This carbon here is the left subside of the alkyne, so we're gonna make the bromine go there. This triple bond becomes a double bond. Yeah, right. Where this is 1, 2, 3. 1, 2, 3, 4, 5. There was a triple bond between 4 and 5. That triple bond became a double bond between 4 and 5. And at the left side, we attached the bromine there because this is anti-Mark reaction with the roar. Now, the next step, we put an Mg, which is an insertion reaction. The Mg here is just going to insert itself between that carbon and bromine, giving us this Grignard reagent here. Right. If we have this Grignard reagent here, what is the charge of this carbon attached to the Mg? Yeah, partial negative, which is our nucleophile. Let's bring in the third step. What is the partial charge of this carbon here attached to the bromine? Yeah, partial positive. Nucleophile, electrophile. Nucleophile, attack electrophile, kick out the leaving group, SN2 reaction. Okay. And that gives us, and the MGBr just floats away. Okay. Star, dot, neo bond between the star and dot. Draw what's attached to the dot, which is CH2 and then isopropyl. Final answer. Yeah. The side product would be Mg2 plus and Br minus. Oh, right, here. Yeah, they would do ionic bond together. Yeah, but we don't have to draw that in the product, but this is what happens. Yeah, to actually understand like everything what's happening and everything. Yeah, that's good. Uh-huh. Oh, this diethyl ether here is a solvent. Because the magnesium here can just exist by itself. It has to like exist in some kind of solution like water, ether, or some other solvent. We want to use ether because it is like unreactive. Ethers are relatively unreactive, which will not react with that Mg. If you use water or something more polar, then it could react with that Mg, destroying it. We want to put it in a stable, unreactive solvent. This or some kind of other non-reactive solvent. But when you do synthesis, right, you don't have to include the solvent. You can just put Mg and you get full credit for that. This is just for completion, like for what's actually happening, right? But that's a good question. Yeah, next one. Any questions on this one? Okay. Oh, nice. Everyone got it. Okay. You guys need explanation on this? Okay, that's good. Yes, this is one reaction where all those reagents are in one step. Like all those reagents are one reaction, yeah, with alkyne. Oh, they are. Oh shoot. Yeah. Dang, I think I yeah. Yeah, actually, I put that there because I made this right before the review session. So for this reaction here, when you see HgSO4, H2SO4 water, this is a hydration reaction of alkyne. This is going to be Markovnikov, right? When you see Hg, think of oxymercuration, demercuration in the alkene chapter, right? That adds alcohol on the more subside. This carbon here is the more subside, so let's add an alcohol right there. Right, after multiple subs. So we have an alcohol here on the more subside where that triple bond becomes a double bond here. This structure here, where you have an alkene next to an alcohol, is an enol. Our enol, alkene next to alcohol. The ene is the alkene, ol is the alcohol. Whenever you have this enol here, it always tautomerizes or converts tautomerization into the carbonyl form. Right. So that alcohol there becomes a carbonyl, carbon double bond oxygen, and we get rid of the double bond here, and we get rid of the H on the alcohol to get this carbonyl form. And the tautomerization mechanism is going to be in acidic conditions because we have acidic conditions in the aryl. It can happen in basic conditions as well, but it won't happen in this reaction. Okay. Where this is the intermediate, the enol, but it tautomerizes into the carbonyl here. And a trick is that if you had a terminal alkyne, right, hydration will always make a methyl ketone. This is a methyl ketone because one of the R groups on the ketone is a methyl group. For internal alkynes, if you have a symmetrical internal alkyne, you only get one product because both carbons are equally substituted. If you had an asymmetrical internal alkyne, then you get a mixture of two products. Because let's say we had like this internal alkyne here. You notice how both carbons here are equally substituted. There's no more substituted carbon. So the ketone could have been on either carbon, which gives you the same product, which is why it's only one answer. If you had asymmetrical internal alkyne, right, where this is asymmetrical because the R groups are different from each other, you're going to get two different products. One product where the carbonyl is on that carbon. The other product is when the carbonyl is on the other carbon here. Right? For symmetrical, if the carbonyl is here, it's the exact same if the carbonyl was here, because everything is symmetrical in this case. Any questions on this reaction? Yeah, excess. Okay, so for this one right here, X2 is halogenation, where we are going to add bromine on both carbons of the alkyne, right? But this is a triple bond. So when we do that, the first equivalent is going to give us the red intermediate first, right? The first Br2 will give us this one here, where one Br attaches to both carbons, but we still have a double bond there. Since we have excess, the second equivalence will react with that alkene and give us this blue product here. Yeah. Right. H2PDC is the reducing agent that would reduce this alkyne all the way down to the single bond alkane. Right. This is the trans alkene, which if we use sodium or lithium metal, two equivalents with ammonia liquid, then that's the answer. This is a cis alkene. So if we use H2 Lindlar's catalyst, we would get the cis alkene. So yeah, there is no oh yeah, there is a typo. There is a typo here. Yeah. Okay, yeah, there is a typo. Dig it. Nice catch. Right. Yeah. Choose the right answer without the alcohol. There's supposed to be an alcohol here somewhere. Like on all of the reactions, there's an extra alcohol somewhere. Yeah. And also, there's supposed to be a third step as well. Acid workup, like H3O plus or H2SO4. Yes. Nice. Uh-huh. Right. Oh, the bottom one here? Oh, you thought that was the alcohol? Yeah. I just shifted that methyl group here. I just like a methyl shift for some reason, but yeah. Right. So MCPBA with alkene, it makes an epoxide. Right? The second step is NaOET, which is that negative charge base right there. When we have negative charge, that's basic conditions. And in basic conditions, we attack the less subside. So we attack that carbon of the epoxide, break open the ring there, and get this right here, right? Where this was the OR that attacked the left subside, and this was the oxygen of the epoxide. Where I was missing that oxygen in the answer. That oxygen was supposed to be there. Right? And we bring in the third step, acid workup, to neutralize the O minus. And this could be been a wedge or a dash, so we could say racemic. Yeah, acidic will attack the more subside. So if this was ETOH, H2SO4, and water, then it would attack this side instead. But since we have negative conditions because of the Na, we are in basic conditions, which attacks the less subside of the epoxide. Yeah. We got the alcohol. Oh, nice. Oh wait, no. Oh, wait. I got tricked. I got tricked. I thought never mind. Yeah. Yeah. Right. So that was a trick question. The hydrogen was not anti. Oh, on the actual exam one? Dang. Yeah, and you got it. Yeah, that's good. That's good. Right. So we have a small, strong base, strong nucleophile, and a good leaving group. We have to look for the beta carbons. This is the alpha carbon because that is the first carbon attached to the leaving group. This is the beta carbon, and that's the beta carbon as well. For small, strong base, strong nucleophiles, we want to make the Zaitsev alkene, the more substituted alkene. But we know that this hydrogen here is a dash because this methyl group is a wedge. On this side, the hydrogens can be wedge, dash, and flat. Right? But we have a small base, so we want to go for the more substituted beta hydrogen. But this hydrogen here is not anti to the leaving group because they are both dashes. So a shortcut here is that we could just do it incorrectly first. Grab that, make a double on there, take that out. Get the wrong answer first, which is this. This is the wrong answer because that was not anti to the leaving group. Once we get the wrong answer, we swap these two groups to get to the right answer. Which is this right here. The reason why this is the right answer is because we know that this is a single bond right here, that can rotate. And I'm going to rotate that single bond because I want to make this hydrogen right here anti to the leaving group. So I want that hydrogen to be a wedge. I'm going to rotate these three groups right here: the hydrogen, the methyl, and the isopropyl. Since I want the hydrogen to be a wedge, I'm going to move that hydrogen to the methyl position. And then this methyl group here is going to become flat. And then the isopropyl here is going to become dash. Everything on this side stays the same. Right? So when I rotate that, this is what I get right here. The wedge bond is now the hydrogen because I moved the hydrogen there. The flat bond is now the methyl because I moved the methyl there. Right? The dash bond is now the isopropyl group. Yeah. Everything here stays the same. Right. Does this part make sense on how I got to this rotated structure? Right. So I just rotated those three groups to make that hydrogen anti to that leaving group. Once that is anti, we could do the normal P2, which gives us the right answer there. Where the isopropyl is down here, the methyl group is up there. Yeah. Oh, right. The isopropyl group is dash because when I rotated these three groups right here, I moved this dash hydrogen to become a wedge hydrogen. That forces the methyl group that was wedged to become flat, which is this methyl group right here now. Then the isopropyl group here has to go to become a dash. Right. So think of this single bond right here, rotating it where those three groups are rotating into each other's spots. Like you're holding the stationary, and then like these three groups are rotating. Oh, like this right here? Yeah. Right. That's the substrate of that beta carbon. Right. Yeah. Yeah, this was tricky because of the anti-periplanar transition state. Yes, nice. Where the H2 Lindlar's catalyst gives us the cis alkene. The trans alkene will come from sodium or lithium metal, at least two equivalents with ammonia. Yeah, no problem. Oh. Oh, yeah. Oh, nice. Okay. Yes. Right. So BH3, think of hydroboration-oxidation, anti-mark, less subside. Right. But we have a triple bond, so the intermediate would be like that, alcohol on the left side, but that triple bond becomes a double bond, where we see that this is an enol, which will tautomerize into the carbonyl form. Like that, where this is an aldehyde right here. So whenever you have a terminal alkyne and you put that through hydroboration oxidation, you always have an aldehyde as a product. Right? But you can think of it as hydroboration oxidation for alkene, which adds alcohol on the left side. And then once you have this enol, alkene next to alcohol, tautomerized into the carbonyl. Right? Where this hydrogen here is that hydrogen right there. Yeah. Br here. Oh, this OH here. Oh, this one here. No. Right. Right. Because this OH here is a neutral weak nucleophile. If you deprotonate it, let's see. 1, 2, 3, 4, 5, 6, 7. Yeah, you can't make a ring because this thing is in the way here. But if there was a bromine here, then there would be a reaction if you deprotonate it. Right? But not here. That's too far away. Yeah. Feminine alkyne. Oh, right. So if it was an internal alkyne here, then yeah, two products, right? Ketone here and there. Hydration. Right. But the better way to do this is hydration because this introduces radicals, which is unstable. This is mostly used for terminal alkynes only when we want to make the aldehyde. Yeah, but that's good. Like if this was asymmetrical internal alkyne, then you get two different ketones. PCC is an oxidizing agent which oxidizes alcohols. Oh, are you talking about like this is alcohol to the aldehyde here? Oh, right. So this right here is tautomerization. This is a new thing. Right. No, it's just like the. Oh yeah, It's like PCC, right. Yeah, primary alcohol to aldehyde. It's like PCC, but the mechanism is not PCC. Yeah. That's right. Yeah, it's like PCC. Okay, now vocab. This one requires you to know about the mechanism of these reactions, like the intermediate, what kind of thing is formed in between the reactant and product. Oh. Oh, okay. No. Right. So hydrogenation, this one here, it's like H2PDC. H2PDC is syn addition. The hydrogens attack on the same side, right? But it is not anti-addition because it's asking for both syn and anti. That is dissolving metal reduction, not hydrogenation. Yeah, that's the ROOR. Where what's the mechanism of this here with the ROOR? What intermediate is formed? Yeah, that's the regiochemistry anti-Markovnikov, right? Yeah, this is the name of the reaction, radical halogenation. But what is the intermediate that's formed? Is there a ring that's formed, like a radicals formed? Yeah, yeah, right. So when you see this, right, somewhere in the mechanism, there is a radical. What is the hybridization of this radical here? sp2, and sp2 atoms are flat and planar. So when the radical attacks with the Br can be on the top or bottom side, syn or anti-addition, right? Halogenation is always anti. Hydroboration-Oxidation is always syn. Yeah, this one here could be syn or anti because of the radical, the flat radical. Oh yeah, and the reactants for all of these reactions are going to be alkenes. Alkenes. It starts with an alkene and then the reaction. Oh, the red one here is going to be HBr and ROR. Yeah, radical addition HBr. Yeah. Oh, nice. Right? Where alcohol addition in presence of H+O4 looks something like this, where let's say we have this alkene and we put that through like this alcohol, H2SO4. This is hydration reaction, and this is the nucleophile, which attacks the Markovnikov position, because when we proteinate this alkene, we want to form the more stable carbocation, which the nucleophile can attack the more sub side. Nice. Oh, nice. Right. Hydroboration-Oxidation of an alkyne will add an alcohol on the left subside, but that alcohol will be right next to the alkene because it came from the alkyne. The alkyne gets reduced to alkene by adding the alcohol there. That's the enol. The enol will tautomerize. For bromination of an alkyne, right, the intermediate is going to look something like this. Like let's say that we have this alkyne and we put Br2 excess. It first becomes this intermediate right here after the first equivalence, but this is not an enol. There's no alcohol here, so no tautomerization, right? And then we just go all the way down. Yeah, nice. Okay, that's it. Yay. Okay. Okay. Let's do Diels-Alder now. Diels-Alder. The speed run Diels-Alder. Okay. So the general reaction of Diels-Alder is you have a diene reacting with a dienophile. You put that under heat or light, you get a cyclohexene. So a diene is two alkenes like that. A dienophile is an alkene that loves dienes. So this is a dienophile. This is diene. put that under heat, right? We get this cyclohexene here, where we have a 6-membered ring and an alkene in the ring, making that a cyclohexene, not cyclohexane, because we have a double bond there, right? So the mechanism of this is going to look something like this. That's it. That's the mechanism. Where let's number this 1, 2, 3, 4, 5, 6. That is 1, 2, 3, 4, 5, 6 right there. Right. It might make it easier if I color code these bonds. Let's say that this bond right here is pink. That pink bond is this pink bond right here. I moved that pink bond to make a bond between 1 and 6. Before, there was no bond between 1 and 6, but now there is, because of that pink bond that moved and made a bond between 1 and 6. Right? There used to be a double bond between 1 and 2, but now there's no more double bond between 1 and 2 because we moved that bond to make the bond between 1 and 6. Yeah. Oh, this is electrophilic, and this is what? Yeah, I'll get to that after I explain to this this thing. Yeah. Right. So let's color code this green. That's gonna be that green right here. Let's color code this purple. Oh wait, no. Purple. This purple. This is green. Right there. Okay. So dienes are usually the nucleophiles in this reaction, and dienophiles are the electrophiles in the reaction. Right. So let's make the mechanism more clearly. Right. Let's say we have that diene right there and draw its resonance structure. We could move this double bond to make a double bond there, forcing this double bond to go to that carbon right there. And that gives us this resonance structure here, right? Where this carbon lost the bond, positive charge. This carbon gained a lone pair, negative charge. This double bond here came from that double bond right there. Now let's draw in the resonance structure of the dienophile. Let's move that double bond on top, making a negative charge on top, positive charge on the bottom. So these are the resonance structures of the diene and the dienophile. We know opposite charges attract, like negative charges are attracted to positive charges, and like charges repel. Negative charges repel negative charges, positive charges repel positive charges. This is the nucleophile here because it's negatively charged. This is the electrophile here because it's a positive charge. We could draw that nucleophile attacking that electrophile right there, and the same for the other side. This nucleophile up here can attack that electrophile right there. Right? When that happens, we form that cyclohexene there. So this is another way to look at it with the charges, right? Where these are the two new bonds right here, the two new bonds between the nucleophile and electrophiles. Right? Okay. Yeah. All dienophiles. Well, it depends. For this case, yes, but there are groups that can be attached to these called electron donating groups or electron withdrawing groups, and that will affect the charges on these right here. And we're gonna go over that right now. Actually, we're gonna talk about EDGs and EWGs now. Right. So EDG versus EWG. So an EDG is an electron donating group. So if you have an EDG, that group is going to be partially negative charge or fully negative charge with a lot of electrons in it. If it has a lot of electrons and a negative charge, it is going to be a nucleophile, which can donate electrons, right? So to tell if something is an EDG or EWG, look at the atom directly attached to the diene or dienophile. If the atom directly attached to the system, either the diene or dienophile, is partial negative or fully negative charge, then it is an EDG. Exception is any R group, like hydrocarbon chain, like a methyl group, ethyl group, isopropyl. R groups are EDGs inductively. And it will be more clear if we go over examples, but these are the definitions here. Where electron donating groups have a lot of electrons and negative charge that it could donate electrons. Electron withdrawing groups is the direct opposite. Electron withdrawing group, EWG, is when the atom directly attached to the system is partial positive charge or fully positive charge. So if it is partial positive charge or fully positive charge, it is an electrophile that wants to gain electrons. Yeah. Yeah, that's correct. That's another way to think about it as well, because the lone pair gives that atom a partial negative charge or a full negative charge. R groups are EDGs inductively, and halogens, right? They are really electronegative, so they withdraw electrons there. In a pi system, like an aldehyde or ketone, that carbonyl carbon is partially positive, making it an electron withdrawing group. So that's another way to think about it. That's a good way. Right? Where halogens are EWGs inductively. Let me put that down. Actually, that's good. That's good. That's good. Let's say EDG, EBC, lone pairs of electrons or R groups. EWG, pi bond, or halogen. Shortcut. Okay, let's look at some examples. Since we said that the diene is the nucleophile in this case, the diene is going to be faster with EDGs. So diene with EDGs will increase the reaction rate. Dienophile is an electrophile, so a dienophile with EWGs will make the reaction faster because electrophiles want to withdraw or accept electrons, which are EWGs. Nucleophiles want to donate or attack with the electrons, which makes it a better nucleophile if we have EDGs donating electrons, making that nucleophile more negative, right? So let's look at these examples here. Say we have that diene with that OR group right there. We know that this oxygen here has two lone pairs of electrons. Those two lone pairs of electrons can directly donate electrons into the diene like that, which is why this is an EDG. Another way you could think about it is that this oxygen here is partially negatively charged because it is more electronegative than the carbons. So it can donate electrons. But the better reason is because it has lone pairs of electrons here that can directly donate electrons through resonance. Yeah. 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 Oh, these arrows here. Oh, these ones here. Right. Yeah. Okay. More examples of EDGs would be any R group, like a methyl group there, right? It could be an isopropyl group as well. These R groups donate electrons inductively, like that. Another example of an EDG would be NH2, because that nitrogen there has one lone pair of electrons that can donate electrons directly to the benzene ring. I mean, not the benzene, to the diene, right? And that nitrogen is also partial negative. Okay, one more example, and then let's look at EWGs. So be careful here, because the atom that you are focused on is the first atom directly attached to the system. Some people might say this is an EWG because they see a pi bond there, but that pi bond is not the first atom attached to the system. The first atom attached to the system is this oxygen here that has electrons and partial negative. So that's an EDG. Now let's look at EWG examples with the dienophile. That could be like a pi. So the first atom here attached to the system is that carbon right there. The partial charge of that carbon is partial positive. And we said that if the atom is attached to, the first atom attached to the system is partial positive or fully positive, it's an electron withdrawing group. Another thing that you can see is that it is pi bonded to the oxygen. Right? Since this is partially positive, it wants to withdraw electrons from the system because it wants to gain more electrons. So that's the resonance for that. Another thing that you can see is CN, nitrile, which that nitrile looks like this, a C triple bonded to nitrogen. This C is also partial positive, and it has 2 pi bonds to nitrogen. So that will also withdraw electrons from the dienophile. Another one that you can see is NO2 right there, where I'm going to draw out that NO2 Lewis structure to see why that is an EWG. The first atom here that is attached to the dienophile is that nitrogen right here. This nitrogen has a full positive charge. So this is the strongest EWG that you could have, NO2. Right? And don't confuse that with NH2. NH2 is an EDG, NO2 is an EWG. So let me make a note of that because that is a common mistake. NH2 is an EDG, NO2 is an EWG. The reason is because that nitrogen here of the NO2 is positively charged, and the NH2 here is partial negative charge with the lone pair of electrons. The NO2 here has no lone pairs of electrons to donate, so that's why it cannot be a donating group. It has a positive charge, which can withdraw electrons from that dienophile. Okay. Okay. Any questions on the definitions of EDGs and EWGs? Okay. These things here will affect the regiochemistry of the Diels-Alder reaction. Regiochemistry. Okay. And let me give you an example of that. So let's say we have this diene with that group here, this dienophile with this group here. Okay. What is this group here? Is this an EDG or an EWG? EDG, right? Because it is partial negatively charged and it has two lone pairs of electrons. How about this group here? EWG. That's right. So this is EDG. This is EWG. And the reason why is because that first atom directly attached to that dienophile is partial positive. Yeah. Uh-huh. Mm. Not always the case because your dienophile could be like that as well, right? Where this is the dienophile, the first atom attached to that is that oxygen with two lone pairs of electrons that is partial negative charge. So not always the case. The one that I've been giving makes the reaction faster, the Diels-Alder reaction faster. This group here on the dienophile makes the reaction slower because we want the dienophile to be the electrophile, but this makes it a weaker electrophile because this is an EDG right here, right? So it's not always the case, but most of the cases, yes. Yeah. Uh-huh. Um, Probably not, no, because the regular diene and the regular dienophile with no groups at all, right? That reaction can barely happen by itself. Then it wouldn't happen. Yeah, right, right. No reaction. Right. So if you have something like this, too, where this is EWG, this is very bad, very bad. No reaction. Yes. Uh-huh. Yes, 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 it does. The dienophile, if there are two groups here, like it wouldn't matter if it's cis or trans. Oh, like the S cis and S trans. Yeah, it would matter because this is the S trans here which would not work, and that's because of the homo-LUMO orbitals, which I'll go over in the next session. The homo-LUMO stuff. Uh-huh. Yeah, the benzene would be considered EDG because a benzene would be considered as an R group. Mhm. Oh wait. Yeah, yeah, yeah. You can. Yeah. Okay, so we know that this is an EDG, which can donate electrons to the diene. So let's draw that donating effect here, where that oxygen is going to do this resonance structure here. Right? We're going to make a double bond here, move that double bond there. This kind of resonance structure here. So this is the resonance structure of this because the EDG donates electrons to the system, pushing the electrons all the way down to that diene, where we have a negative charge down here. This is an EWG, which is going to withdraw electrons from the dienophile. So the resonance structures will look like this, where that dienophile's electrons are being withdrawn from this EWG here. When that happens, we get this resonance structure here, where because this carbon here lost the bond, that carbon has a positive charge right there. Right? Okay. So now let's focus on the backbone of the diene, which is this one here, and the backbone of the dienophile, which is that one right there. Let's focus on the charges. We see there's a negative charge down here and a positive charge down here. If they align, then the reaction would go through, right? Because opposite charges attract, like that. Where I'm going to draw out the diene with that EDG like this again. and the dienify with that EWG like this again, where we know that there is a partial negative charge here and a partial positive charge here. Okay. Since there is a positive charge up here, I'm going to say that this was the partial positive carbon up there. And since there's a negative charge up here, I'm going to say that there's a partial negative charge here. We see that the charges do align and attract because opposite charges attract. This reaction can go through, right? So we do the regular arrows for the mechanism, like that, which will give us this product right here, right? Okay, so that is the regiochemistry, but now for stereochemistry here, this is talk about the endo and exo rule. A lot of people might think that they have to be trans to each other, right? They might say this is dash, that makes this a wedge aldehyde. But this is not the major product, right? Have you guys learned about the endo-exo rule in class yet? No? Oh, okay. Yeah. So this seems like the major product because you know how they're trans and there's less steric hindrance? This is actually the minor product. The major product would be if they're on the same side. So let me show you why. So this is the major product right here. Major. And this is minor. OCH3. H. Okay, so the reason why is because, let me make more space. Copy. Let me put that down here. Okay, let's say that I'm going to draw in the diene like this with the OCH3 group and a dienophile down here with the EDG. You know how there are p orbitals on these atoms right here that are sp2, 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 right? Those p orbitals there want to be aligned to each other, right? So they want to be closer to each other, so on the same side. When we do this mechanism here, we are going to have this product where the two groups are on the same side because that increases p orbital overlap, right? Which overpowers the steric hindrance factor. Right. This one right here, since the groups are opposite from each other, they have less p orbital overlap. When you think of p orbital overlap, just think of resonance. Like they could do more resonance with each other. Less resonance in this case, right? Because you know how resonance happens between sp2 atoms or p orbitals where the electrons can hop to different p orbitals, right? We want the p orbitals to be on the same side so the electrons can hop onto the next p orbital and do more resonance, which gives us the groups on the same side to increase p orbital overlap or resonance. Even though the steric hindrance factor is worse in this case, the resonance factor is greater, which overpowers the steric hindrance factor. The steric hindrance factor here is better because there's less steric hindrance, but there's less resonance because the p orbitals are not aligned anymore. There's less resonance here. Yeah. Oh, not always ortho because let's see, negative charge here. It depends on how many groups are in the dienophile. If there are two groups, then we would also have that group right there. And also, your EDG could have been on one of these carbons as well, right? So if it's in one of these carbons, then it could be para or meta. Yeah, if there's only two of them here, right? Then they're ortho to each other like that, right? Right now we're just like starting with the basics, and then we'll put on the difficulty as we do more examples, right? where I'll show you guys this right here. He could trick you guys by putting this on the test. He could give you that EDG, and he could give you this EWG right here. Right? A lot of people would do this. They get the stereochemistry right, which is the same side, but the regiochemistry is wrong. Because you notice how when we did the resin structure, we know that there's a negative charge here, positive charge here for the diene, and for the dienophile, there is a positive charge here, negative charge here. Do these charges align, attract to each other? No, they do not. So this will not happen. What you have to do first is you have to flip one of them upside down to make them align. I like to flip the dienophile because that's smaller and easier to flip. When I flip that, now the charges will align, right? And when the charges align, we could do the correct mechanism now, which will give us the correct product on the right spot, right regiochemistry, where the aldehyde is up here and the polarization is up here, ortho to each other, right? Not meta, because the charges do not align, right? Here, repulsion. So flip one of them upside down to make them align to get the correct answer, the correct regiochemistry. And we'll do more examples of this where the EDG could be here or here, and if the dienophile has more than one group, next session with the homolumo as well. But that's an introduction of the regio and stereochemistry of that. Okay, that is it. Any questions? Oh yeah. Let me sign you guys in really quick. Thank you for reminding me. Yeah. Dienophiles, yeah, all dienophiles have an alkene. Can you sign in, please? And all dienes have a conjugated diene. Right. All dienophiles have one alkene. All dienes have one conjugated diene. So diene is two alkenes. So diene has to have two alkenes. Dienophile has one alkene. Yeah. Hi, have you signed in? Okay, thank you. Yeah. How is this stuff so far? Like, is it like okay so far, or is it confusing? Like with the Diels-Alder. Oh yeah, I see. Yeah, the homolumo orbital stuff. Oh my gosh.